All right, today we're jumping into a topic where there's absolutely zero room for error. We're talking about the life-saving safety rules for working with high voltage on offshore vessels. So, let's get straight into why these procedures are so critical.
And let's be totally clear about the stakes right from the get-go. The official guidance does not mince words here. Contact with high voltage is pretty much a guaranteed fatality. This isn't about getting a little zap or a minor injury. This is life and death. And that's exactly why every single rule we're about to cover is non-negotiable. So, to really get a grip on this, here's how we're going to break it down. We'll start with the raw power and risk of high voltage. Then we'll get into the paperwork that literally keeps people alive, the permit system. From there, it's all about the hands-on procedures, uncovering those invisible threats, and finally, seeing how it all fits together into one system that's designed for one thing: survival.
Okay, first up, power and risk. You know, as vessels have gotten more and more powerful, especially those huge offshore construction vessels, their electrical needs have just gone through the roof. The old standard 440-volt system, well, it just can't keep up anymore.
And this slide right here, it tells the entire story. To get 1 megawatt of power, which you need for major equipment, a standard low-voltage system has to deal with a whopping 1,640 amps. That's a massive amount of current. But now, look at the high-voltage side. By cranking the voltage up to 6.6 kilovolts, you get the exact same power with just 109 amps. That is a gigantic reduction. It's not just a small improvement, it's a complete game changer.
And this is why it's such a big deal. Lower current means you can use smaller, lighter, and more efficient cables and motors. You waste a lot less power as heat, and, maybe most importantly, it's what makes it even possible to run the incredibly powerful equipment. We're talking giant thrusters and cranes that these modern offshore vessels absolutely depend on. So you see, high voltage isn't really a choice, it's a necessity.
So, we get why high voltage is essential. Now let's dig into the foundation of how we work with it safely. The absolute first step, before a single tool even comes out of the box, is a really strict administrative control.
And that control is the permit to work, or PTW. Now, this is not just a piece of paper. It's not a bureaucratic box you just tick. Think of it as a formal, written contract of safety. It is a declaration signed off that states with absolute certainty what specific piece of equipment is dead, isolated, and safe to touch. Without this document, no work starts. Full stop. The whole permit system really relies on two very distinct roles. First, you have the Authorized Person, or AP. They're formally trained and appointed to oversee the system and issue the permit. Then you have the Competent Person. This is the technician, the one with the skills to actually do the job safely, who receives that permit. This separation of duties is in itself a crucial safety check.
Okay, now we get to the physical actions. Once that permit is signed and issued, there is a strict step-by-step procedure that has to be followed every single time to de-energize equipment and make it safe.
And the heart of that procedure is captured in a simple, life-saving acronym: LIVE. First, locate. You have to identify every single possible source of power, including any backups. Miss just one, and the whole thing is pointless. Next, isolate. You securely disconnect it and lock it out. Then, verify. This is the moment of truth. You use a meter to prove, not assume, but prove that the circuit is dead. And finally, earth, to drain away any hidden stored energy. Locate, isolate, verify, earth. You have to follow every step, in order.
And when we say isolate, we don't just mean flipping a switch and walking away. We're talking about a secure, physical disconnection. This is usually done with safety locks that have unique keys. And those keys? They're then placed in a controlled key safe, which is managed by the authorized person. This makes it physically impossible for someone to accidentally re-energize the equipment while you're working on it.
And that leads us to the final, absolutely critical step: earthing down. See, even after a circuit is turned off, it can act like a capacitor, like a little battery, holding on to a lethal charge. Earthing connects that equipment directly to the ship's hull, which creates a safe path for any of that stored energy to drain away, bringing the system to a true, safe, zero-volt state.
This brings us to one of the most important, and frankly scariest concepts in high-voltage safety: the hidden threats. Just because a breaker is open, that does not mean the danger is gone. Not even close.
And listen to this quote, straight from a safety manual. It's chilling, but it's a fact.
A fatal charge can hang around on high-voltage equipment for hours, or even days after it's been disconnected. This is that invisible killer that makes the earthing procedure so absolutely critical.
So how is this possible? Well, it's just physics, but physics with deadly consequences. High-voltage cables act like capacitors. They store energy. Now, look at this formula. The really important part is that the stored energy is proportional to the voltage squared. Let me say that again. The voltage is squared. That means if you double the voltage, you don't just get double the stored energy. You get 4 times the stored energy. So now imagine going from 440 volts to 6,600. The amount of invisible, lethal energy just sitting there in that dead cable is astronomical. It's a silent threat you have to respect.
And the hidden dangers don't stop there. A live cable running nearby can act like a wireless charger, inducing a lethal voltage back into a circuit you just proved was dead. Your own test meter can turn on you. If it's not earthed properly, the entire casing can become live right there in your hands. Even just being wet lowers your body's resistance so much that what might have been a survivable shock becomes a fatal one. The entire environment is filled with potential threats.
So, as we start to pull all this together, it becomes really clear that high-voltage safety isn't about one single thing. It's not a gadget or a single rule. It's a complete, multi-layered system where every single piece has to be perfectly in place.
And here's how all those defenses work together. You've got physical barriers like locked enclosures. You have administrative controls, which is the permit to work system. You've got that mandatory procedure: isolate, verify, earth. You've got clear warnings, danger notices. And right at the center of it all is the human element, making sure only trained, competent people are ever allowed near this stuff. Each layer is there to catch a mistake before it turns into a tragedy.
And that's really the key takeaway here. This isn't about a single action, it's a discipline. It's a documented process that you have to follow with extreme care every single time. Every step, from that first signature on the permit to the final clamp of the earth connection, is another critical link in the chain of survival. Look, the procedures are rigorous, they are detailed, and they demand your full attention. But after everything we've covered today, from stored energy to induced voltages, the final question is a pretty simple one, isn't it? What is the cost of skipping just one of those steps? In the world of high voltage, the answer is terrifyingly clear.